Hi everyone. Today we're taking a look at a high-resolution row vibrational infrared spectroscopy investigation of HCl and DCl. Before we get into it, I want to just quickly note why it's important that we're using high-resolution infrared spectroscopy, especially because throughout a lot of our undergraduate careers, we tend to think of infrared spectroscopy as something mostly associated with vibrations, and we would expect to see these big, wide peaks. That's not the case for high-resolution infrared spectroscopy, where the rotational transitions are also resolved, so we can see a much more elaborate and informative spectrum. That's important because one of our objectives is just to obtain a rotationally resolved vibrational absorption spectra of HCl and DCl. From that spectra, we are seeking to determine physical constants and parameters that describe the rotation, vibration, and dissociation of these molecules. And it looks like a lot here, but we can break it down very simply. Starting off just with HCl, we know that it can undergo vibration, as can DCl. And we know that we can describe this vibration approximately through the harmonic oscillator model. Here, it's possible to relate X, the change in internuclear separation, to K, the force constant, and energy to the degree of vibrational excitation, to Planck's constant, and the harmonic frequency. So here we're already able to determine two of our constants or parameters of interest. Next, we can look at rotation because we know that that is also relevant for HCl or DCl, and we can approximate this using the rigid rotator model. Here, we're able to relate energy to Planck's constant, the speed of light, the rotational quantum number, and the rotational constant. With this equation, we can also express the rotational constant in terms of how it relates to inertia, and inertia is composed of reduced mass and the equilibrium bond length. Because it's very easy to calculate the reduced mass from just known masses of the atoms themselves, we're able to find the equilibrium bond length from our data. But that's not all. We also need to think about dissociation, because that's a real possibility for both HCl and DCl. And we need to consider all of these three ideas together because they impact one another. We can start off by thinking about the Morse potential, which you'll notice looks kind of a lot like the harmonic oscillator if we look on the left, but on the right, not at all. This is because as atoms get closer and closer together, they can only get so close because we have strong internuclear repulsion. But they could get infinitely far apart if they undergo dissociation. So here we can describe dissociation and determine bonding energy and the potential energy to the bottom of the well. By bringing in another helpful couple of equations that relate variables that we previously defined to some new terms that tell us how these different models interact with each other and influence each other, we are able to define anharmonicity as well as rotational vibrational coupling constant and the centrifugal distortion constant. This is going to describe how much non-rigidity of the bond impacts rotation. We're ready now to come up with a few hypotheses. Firstly, we believe that the equilibrium bond length should be the same for HCl and for DCl because the atomic radii are the same for hydrogen and deuterium. We're not impacting the electronic configuration, the charge, or anything that we would expect to have a profound impact on bonding. Secondly, this is relating directly to our equations. We think that the rotational constant for HCl should be approximately twice the rotational constant for DCl because they depend inversely on reduced mass because of their dependence on inertia. Now we can take a very quick look at our methods. Starting out, we have 2.5 grams of potassium chloride in the bottom of a round bottom flask. Then that is equipped with a 3-way adapter and a septum. We should note the stopcock is open because our goal is to produce HCl and DCl as gases. They need to be able to flow through this system. Secondly, this tubing here is clamped securely on both sides and connected with a needle to our gas collection chamber. This is equipped also with septa and a needle for venting because we're going to be displacing the gas that was previously in there. We're not trying to build up a bunch of pressure. Next, for making our mixture of acids that will be undergoing the chemical reaction with our salt, the 1:2 ratio of sulfuric acid to deuterated sulfuric acid. And it's important here that we need to go fast because These are both hygroscopic. We don't want to undergo a lot of exchange between our deuteriums on our deuterated sulfuric acid with hydrogens from water from the atmosphere. That will mess up the experiment. The next step, it's important to go slow. When we're doing the addition of our acids onto our salt, we're going to be producing gas. So we're going to get this sort of frothy mixture, and you don't want that to exceed half of the volume of the flask. It unfortunately did, but at that point, it's important to absolutely make sure that it does not enter the gas collection chamber and to make sure that you do the appropriate cleanup. Thankfully, it did not, so we can look at our methods and our data. Methods, very quickly, we used a Perkin-Elmer FTIR spectrometer where we use an IR light source going through a beam splitter and interacting with a fixed and moving mirror, which the distance of the mirror is recorded and used in processing the data. After it goes through the sample onto the detector and interferogram, we can interpret the degree of constructive and destructive interference in the IR radiation, the infrared radiation, and then the computer is able to use Fourier transform to convert from the time to the frequency domain, and then we have useful data. So let's look at our data. Here is the full spectrum, and first we might immediately notice that we have these 4 clusters, and each of these clusters, shouldn't be surprising, represents vibration, and then the little peaks making them up are the rotational energy levels that are more narrowly spaced. Here we can also assign HCl and DCl based off of their wavelength, and overtone and fundamental transitions based on both the wavelength and the population. So what does that mean? Let's take a look at the fundamental HCl transition. Here, zooming in, we might quickly notice that there's 2 obvious branches, our R branch and our P branch. Secondly, we might notice that each of our rotation peaks is further split. That's because chlorine also has 2 isotopes, but the difference in changing chlorine isotopes only very slightly impacts the reduced mass, which is why we see such small splitting here. Getting back to our R and P branches, these are all representing the same vibrational transition from the ground to the first excited state, but the rotational transitions that also are represented change. From our R branch, we're going from J to J plus 1, and P branch, we're going from J to J minus 1. This is an important distinction, and we might also wonder, what about going just from J to J at the next vibrational level? That would be the Q branch, and in most systems, including this one, it's a prohibited transition. We can see that there's no peak in between our 2 branches. So let's zoom back out for a moment and then focus on an overtone transition. Overtone transitions have the same R and P branch relationships, but instead of going to the first vibrational energy level, they're going to the second. These transitions are actually prohibited in harmonic models, and they're only made weakly possible because of anharmonicity. That's why we see such a smaller population. It's also important to note here before we move forward into processing our data more completely that the separations in energy are non-linear. And specifically for our P branch, as we're increasing in our J value, we're getting more and more separation between these transitions. Contrastingly, in the R branch, when we're increasing in our J value, we're getting narrower and narrower placement of these peaks. We're able then to look at our data from the branches individually, and we can apply a 3rd-order polynomial regression equation. Then we can compare that with equations describing our variables that we're interested in and use the coefficients on each term to directly assign D, alpha, and B, the centrifugal distortion constant, the coupling between rotation and vibration, and the rotational constant. Then we're able to solve a simple system of equations in order to determine our harmonic frequency and our anharmonicity. From there, we then have these values for the P branch and the R branch for each of the fundamental, and the overtone value for HCl and for DCl. But for better clarity, we can look at a summary of HCl altogether versus DCl altogether. Here, let's start by returning to our hypotheses. So the rotational constant did in fact depend inversely on the moment of inertia, and we saw a larger reduced mass resulted in a much smaller rotational constant for DCl compared to HCl, which has about twice the reduced mass of HCl. That makes sense, and we included percent differences just so we can easily identify some trends because we see similar behavior with multiple other variables, D and our anharmonicity. Contrastingly, we found that the bond length did not depend on the reduced mass, and that's also consistent with our hypothesis because that's related to our electronic structure and bonding. We also correspondingly saw that other terms describing bonding did not depend on reduced mass. So overall, it was possible to probe the transitions allowed between the vibrational and rotational states to determine an important set of constants and parameters. Thank you so much.